Okay, because they're both not very long. I know. Sorry. Yeah, so we'll see. Why is showing that? I don't know how to make this. So yeah, that bottom, it usually doesn't do that, does it? Like have that stuff on the bottom? See if we can make it go away. Well, now everything went away. That's weird. Well, maybe we won't get through 2 parts today.
One can only hope.
That's bizarre. Well, now it went away. That's better. All right.
So it's not back for 2. We're not doing 3 because these 2 look pretty short.
What's that?
They look really short. They look
Yeah. So, good way to think of it is if we get through 2, we're not going to begin with that 3rd part. So, yes.
So ask a lot of questions.
No. Oh, that stuff came back. Oh my gosh. Oh well, we'll just have to deal with it. Ask questions as they come up, not like random questions. Okay. So, what 2 types of ways to talk about solution concentration did we do on Monday? Da-da-da and da-da-da. Moles per solute per liter solution, very good. And then G/L. Grams per liter, yep, those are 2 ways, yep. So definitely in chemistry, a lot of chemistry is about numbers, a lot of chemistry is about concepts, but about numbers. So you're gonna need to be able to use like the concentration of a solution in problems. So the concentration of the solution, if it's given in G/L, that means grams of solute per liter of solution. Okay, if it's given in terms of big M molarity, again, there is a small m in chemistry, and I have no idea why they did that. They're so similar, an uppercase M and lowercase m, but big M is molarity. And then we talked about mass fraction before. So these are physical properties of the solution. And so I always talk about unpacking. And so you're going to, like you said, grams of solute. Let's see. Oh, wow. Grams of solute per liter of solution. This is moles of solute per liter of solution. And this down here would be grams of solute per 100 grams of solution. That's the weight percent. So if you have these in a problem, if that information is given, it's a physical property you can use as a conversion factor. So it looks something like this. So in reading this kind of from left to right, it gives you, that's the physical property of the solution. I'm going to use it. It has to be sodium chloride solution. Sodium chloride is a solute. What volume, so I could put question mark volume, will 22.3 grams of NaCl require? So once I get my units down like that, then I can clearly see that actually this grams per liter will get me there, 14.3 grams per liter. That's how I'm going to kind of accomplish it. So I put it over the arrow. Now, 14.3 G/L, you're always going to want to unpack that and be explicit with regard to your units. So 14.3, in this case, grams of solute, NaCl, per exactly 1 liter of solution. Is there uncertainty in 14.3? Yes. Is there uncertainty in 1? No, because you unpacked it by definition. For this particular solution, the reciprocal is also true. And in fact, we're going to use the reciprocal in this case because we're trying to go from grams of solute to volume of solution, aren't we? So in 1 liter of solution, it would contain 14.3 grams of your solute. Cool. So the first term is going to be when I say what's specific to the problem. And in this case, it's not the concentrations of grams per liter, it's the grams that you're trying to get to the volume. So I put this over 1. And if we want grams of sodium chloride to cancel in the numerator, what goes in the denominator in the next term? Grams of sodium chloride, yep. So we use kind of the flipped version of the reciprocal of the grams per liter is given. So very good. And I can't remember, did it ask us to go to milliliters or did it just say? Okay, what volume? So we'd be done, right? Okay. Notice that I went ahead and if I were to ask you to show me fingers, you would give me 3 fingers is how many significant figures I should keep. So unit-wise, grams of sodium chloride cancel, we're left with units of moving the solution. That's it. Let's do another one. In this case, we're gonna unpack, capital M means molarity. So here in a minute, on the next slide, I'm gonna unpack that. So that's not what's specific to the problem. What is specific to the problem and is gonna be my first term is 0.015 moles of the solute, which is potassium dichromate, K2Cr2O7, and I'm supposed to get 2 milliliters. And molarity, we unpack molarity and it looks like this. So 0.255 big M means 0.255 moles of K2Cr2O7 per 1 liter of solution. And then the reciprocal is also true for the solution. It's a physical property. And 1 liter of solution, it would contain 0.255 moles of potassium dichromate. So what's going to be our first term? Yep. 0.015 moles of K2Cr2O7 over 1. You guys would tell me if I want moles of potassium dichromate to cancel, I'm going to have to put moles of K2Cr2O7 on the bottom. So that's what I call the flipped version of the molarity. So we're going to use that reciprocal molarity. 1 liter solution or 0.255 moles K2Cr2O7. So how do we get from liters to milliliters? Yep, 1,000 milliliters over 1 liter. And that's it. The moles have canceled, moles of solute have canceled, liters of solution have canceled, and we're left with units of milliliters of solution. So how many sig figs? I got 2, 3, and 4. It's 2. Why is it 2?
Because there's 2 leading zeros.
Yep. These don't count, but this does. And then over here, this doesn't, but that counts. And then there's no uncertainty brought here. So, yep, 2 sig figs. All right. So I get 59 milliliters of solution. Now, a lot of times, this is kind of, chemistry problems, or I should say, in class, I kind of teach you these little things, and then you bring them all together. So sometimes this is a small part of what you need to do to get from point A to point X. Cool. Let's do another one. So how many moles? So I'll put, on the far right, I'll put question mark moles. The solute this time is calcium chloride, CaCl2. Are there in 75.0 milliliters of solution? And it goes ahead and it gives the molarity as 0.108 molar. I should say 0.108 molar with regard to the solute calcium CaCl2. So I don't have a separate slide, but unpacking, what does 0.108 m CaCl2 mean? This is what it means here in pink. So now I've got a few slides that kind of draw you through the process. Notice that molarity is in moles of solute, this time calcium chloride, per liter of solution. So by golly, I'm going to start with milliliters, but I have to get it to liters. I can do that with a factor of 1,000 milliliters is equal to 1 liter. And then I can go ahead and go from liters to moles using the molarity. So what's the first term going to be? Yep, 75.0 milliliters of solution. Perfect. And then what about the next term? Yep. Next term is going to be 1 liter over 1,000 milliliters. Now we're going to use molarity. Will we flip molarity or will we use it as it is? Use it as it is. Yep. 0.108 moles of calcium of CaCl2 over 1 liter solution. Are we done? Yes, we are done. How many sig figs? Why is it 3?
0.108 and 75.0. After this will not significant.
It is significant. Yep. Yep, 3. 3 sig figs. This one is called a trailing 0 after the decimal. So it does count. So 3 sig figs. Okay, so 3 sig figs I get, and you see how this actually gives us 3 sig figs? So the 8 and the 1 are significant, and this 0 on our answer is also significant for the same reason that 0 with 75.0 is significant. This guy right here is the same as this guy right here. And these are not significant. Okay, very good. Okay, another one. So what mass of glucose? So over here on the right, I'm going to put grams of glucose. The formula for glucose is C6H12O6. Is there in 100? And over here on the left, I'm going to put 125 milliliters of solution. And notice we are given the molarity. Well, in the problem we did, maybe it was just before this one, with the 75.0 milliliters, we were able to go from milliliters to liters, and then we were able to go from liters to moles using what? Molarity, yep. And then how are we going to go from moles to grams? Molar mass, mm, yep. Very good. So that's kind of right here. The one thing I don't like about kind of to me, kind of how this built, it went from milliliters to liters to moles to grams. I really like, because sometimes you work backwards in chemistry problems. I really like putting milliliters there, and my goal is grams over here, and I can almost think backwards. Well, I can get, if I use molar mass, I can get from grams to moles, and then I know that I can get to moles from volume and molarity. So what's the first term going to be? Very good, 125 milliliters solution over 1. Now we're going to use, we've got to get to liters. What does that look like? Yep, 1 liter solution over 1,000 milliliters. Very good. And now I'm ready to go ahead and get to moles. Do I use the flipped version or do I use the non-flipped version? The non-flipped version, because the non-flipped version liters is the bottom. Yep. So that looks like this. The molarity was 0.432 moles of C6H12O6 per 1 liter of solution. By the way, if I was doing this, is this sucrose? No, what is that? What did it say on the slide? Glucose, okay. So if I was doing this, I might even write like GLUC. You know what I'm saying? I might even abbreviate it. All right, so we got to moles, and actually then how are we gonna get from moles to grams? The molar mass. And this is where I'm not real happy with my slides, because if you were doing this problem, can that magically appear? If you did that, I'd say, where did this come from? I really would, because that's my molar mass. That's a separate calculation. So, psi. But when I introduce the molar mass, now moles cancel, and of course liters canceled before, milliliters before, so I have grams, which is great. How many sig figs? Consensus is 3. I agree. Cool. So with 3 sig figs, I get 9.73 grams. Does this start to look like a practical thing? Okay. So say somebody says, dude, I need a target molarity of 0.432. That's my target molarity. The volume I want is 125 milliliters. What mass are you supposed to weigh out of glucose? 9.74 grams. So, okay. That concludes part 10. I don't think I could go any slower than that. Sorry. And you didn't ask many questions.
I didn't.
Okay. So let's take a look at part 11. Cool. Again with the concentration of solutions. There's a short video in this one. Look forward. Has nothing to do with this, but like working in a factory, and it's actually illegal. They look at your discharge, your effluent, to make sure that what you're discharging is safe for the environment. And so there's a thing, the solution to your pollution is dilution. It's illegal. And wherever I work, we didn't do it, but you know, if you, for instance, if you can only in your effluent have, so I worked at an ammunition plant, a bomb factory. If you could only have like, 100 parts per million RDX, and you were running 200 parts per million RDX, well then you just dilute it by 2. Anyway, that's what I always think when I think of dilution. So there's this process that starts like this. You have basically, this is ugly, this is my volumetric flask. It's terrible looking. I have a calibration mark up here, so it's pretty precise. Okay, this is your stock solution. Okay, your stock solution is more concentrated, and then what you do is you have another, this is my other volumetric, it's empty, it has another calibration mark. You take, starts with the letter A. What do we call it when you take a small amount of liquid? What? Pipetting. But what about the word, the A word? The pipetting is kind of the verb. What?
Aliquot?
Aliquot. Yep, that was the word I was after. But it is definitely called pipetting. You use a pipette and you take an aliquot. I just like that. So it sounds like kumquats or something. So you take an aliquot of your stock solution, you transfer it over by pipetting, and you put it in here, and then you dilute this up. And then this is your diluted solution. Now, sometimes students are like, well, why didn't you just go for this first? Can you think of any reasons why you wouldn't just go for your diluted solution first? What if you wanted something pretty darn dilute? And let's say, let's make this a 1 liter. What if your solute to prepare that, you were like weighing 0.3957 grams? I don't know, on our balances, that's not a whole lot of material. So already with your stock, your concentrated solution, you're down to 0.3957 grams. Let's just say your aliquot is a 1 milliliter, and you transfer it again to another 1 liter. Let's see, that's a dilution of what, 1,000-fold? So in other words, if you wanted the same over here, let's just think outside, what mass would you bring in here? Is this what you guys are getting? I moved the decimal place over 3 places. Is that right? Oops. The best I can do is like that. Does that make sense? Okay. So we've got that's 0.0040 grams, so I kind of rounded that out. This is problematic. And we kind of talked about kind of relative uncertainty and how much you're introducing a lot more uncertainty here, measuring 0.0040 grams, than you are something you can sink your teeth in. So this is why we do this. And often it depends upon how dilute you really need it to run your experiment or to, do your test or whatever. Sometimes, and it's called serial dilution, where we actually have more diluted here, more diluted here, more diluted here. We take an aliquot gets more and more diluted. So it's kind of fun. Important. Okay, so kind of with that in mind, we're going to do a few problems. And I think on my answer keys, you might see, not always, but these ugly volumetric flasks. And it kind of goes from left to right, stock, and that sort of thing. Because I think a picture really kind of helps. So let's kind of take this and let's make a picture out of it. So that's always going to be my stock. It goes from left to right. And then this is going to be my diluted thing. Oh my goodness, that's so terrible. But that's when we diluted. I think if I took time, they've got to get better than this. So it says there is a 25 milliliters of a 0.160 molar calcium chloride solution. Now it doesn't say stock, but it is. That's the stuff you start with. So I draw a little arrow over and I do 25.0 milliliters of the stock. And underneath the stock, this is why the picture comes in handy, I put 0.160 molar calcium chloride. And now it says it's pipetted into a volumetric flask and then I go over to my right volumetric flask and I put a capacity of 125 milliliters. Now, the fact that it's a volumetric flask, I'm going to go ahead and slap on a couple zeros, 125.00 milliliters, because your volumetric flasks are known to quite a bit. Sufficient water is added, and the way I usually show that is after my aliquot is dumped in, I usually kind of do this. These are my hash marks to show water is added. Okay. So the question here, and I'm going to put a question mark over here under my diluted, it says question mark, what is the molarity? So question mark molarity over here, question mark big M. Sometimes what's helpful is I'll actually unpack that. What that big M is question mark moles of calcium chloride in 1 liter of solution. That's my target units. Whoops. So that's it. Sorry. But this pen doesn't help any, really. Okay. So I think you could do this not breaking it up into parts. I'll go ahead and tell you the parts I'm going to break it up into. Part number 1, I'll put a little 1 up here by my aliquot. Part number 1 is, I'll put question mark moles of CaCl2 transferred while I was pipetting. That's my step number 1. And then actually, step number 2, I'll put over here by my diluted. And I'll say step number 2, all I have to do is take the moles that were transferred and divide it by what I diluted it up to, divided by this, 125.00 milliliters. Now, is moles per milliliter going to give me molarity? Moles per milliliter. It's got to be moles per liter, so I got kind of a cleanup step. That's kind of what we're going to see. So notice in blue here, I actually go ahead and I give my 2 steps a little title, and that's kind of optional. I don't know. I probably would simply call this instead of, I would probably just call it moles of calcium chloride. And then I would take as my first term, by the way, how can we get to moles? We can use the aliquot volume and the molarity of the stock. So my first term is going to be 25.0 milliliters. I got to get it to liters, okay? Because molarity is moles per liters. So how do I get it to liters? Yep, multiply by 1 liter or 1,000 milliliters solution. 1 liter solution over 1,000 milliliters of solution. Now I'm ready, just like we just did in the previous part. Now I'm going to use molarity. I didn't unpack it for you guys, but the 0.160 means 0.160 moles of CaCl2 per 1 liter of solution. Do I use it just like that, or do I flip it? Why people think just like that? Me too. Yep, stick in molarity there. 0.160 moles of calcium chloride. I'm going to ask the sig figs. 0.160 moles of calcium chloride per 1 liter solution. So our units of liters of solution cancel, milliliters of solution cancel. We have transfer moles, which was what I was after in this first step. How many sig figs? Oh, you're all in agreement. 3 sig figs. This is a weird one. So the way this works then is you actually have to go ahead and write what we call 2 trailing zeros after the decimal to get your 3 sig figs in. These are not significant. So what was the next step? Step 2? Yep. Now that we know the transfer moles in this problem, and the problem with dilution problems is there's so many variations. The next one is to knock out the molarity of the diluted solution. And again, if you were going to give this appropriate title, molarity, dilute solution. So yep, we're just simply going to take those moles that we came up with, 0.00400 moles, CaCl2. Notice that I only gave it 1 trailing zero after the decimal. Here, in my figure I gave it 2, but that's okay. 125.0 milliliters of solution was the capacity of our volumetric flask. Now, how do we get it to moles per liter? Yep, multiply by 1,000 milliliters of solution over 1 liter of solution. That'll do it. How many sig figs? Yay! 3 sig figs. So to show 3 sig figs, we're going to go, and this is probably what I would do down here. To show 3 sig figs, we're going to have 1 trailing zero after the decimal. Yeah. Like I said, there's so many different variations. I think we're just going to hit a couple more. All right. Oh, video time. This is a still image of a dilution going on. Or, you know what I mean? Yeah. From left to right, you can see kind of the stock solution there being pipetted. Then it's transferred. I like how the video said, and like you guys have been doing when you did pipetting, you touch it to the side of where you're transferring it, and then you dilute it up with water. And the cool thing, I mean, it makes sense. How would you compare the intensity of the colors of these two? What do you think?
One's more yellow.
One's more yellow, exactly. The stock is more yellow than the diluted. There is a technique called colorimetry, which kind of looks at the intensity of the color and tracks it back to how concentrated the species making the color is. Alright, so let's do another example. Let's go ahead and kind of map it. It's going to have a different twist on it than the other one did. So let's see if I can make it. No, that's still pretty ugly. That's my stock. And here is my volumetric flask it's going to be my diluted. See what information is given. In this case, it says 2 milliliter of stock solution is transferred. So here is my arrow. Of course, I'm going to pipette this. I'm going to put 2.00 milliliters is transferred. The solute is K2CR2O7, potassium dichromate again. It says that my empty flask, I'm going to transfer it over into its volume it goes ahead and it shows you the uncertainty begins in the tenths milliliters, so 500.0 milliliters. That's what I'm going to dilute up to. Enough water is added to bring up to the volume mark. So I add water, I bring up to the calibration mark. Now this one's a little different because it says the resulting solution is 1.60 times 10 to the minus 4th molar. So this is my diluted stuff, right? So over here then on the right, I'm going to put 1.60 times 10 to the minus 4th molar. The solute is K2CR2O7. Where's my question? Oh, so what was the concentration of the stock solution? So I'm going to put question mark molarity over here for my stock solution. Now this one's a little bit different. Do you see though, now we know more about the diluted than we do about the stock. So we're going to actually kind of reverse engineer this. The first thing we're going to do, we know we can use volume and molarity to get to moles. So step number 1 is going to be moles of solute now. Moles of K2CR2O7 in diluted solution. We can do that. And then it's kind of fun because those moles, and I don't know if I can put this in form of a question, but you see where the moles that are swimming around in here, they all came from our 2 mil aliquot. So then all we got to do is step number 2 is to take those moles that were transferred, moles transferred, I'll just put TRANS for transferred, divided by the volume they came from, 2.00 milliliters. Does that make sense? That's it. Moles transferred divided by the aliquot they came from, that will give us the molarity. Of course, not really, because that's moles per milliliter, you can get moles per liter. So here we go. The moles of the solute that must have been in that volume of diluted solution, we take the volume, I start out with the volume, 500.0 milliliters solution over 1. Now how do we get it to liters? I know you're all thinking this. 1 liter of solution over 1,000 milliliters of solution. Now we're ready to plop in the molarity. Remember, the big M means moles of solute per liter of solution, and I want liters of solution to cancel, so I'm going to use the unflipped version. So it looks like this, 1.60 times 10 to the minus 4th K2CR2O7 moles of K2CR2O7 per 1 liter solution. And just looking at what cancels, milliliters have canceled, liters have canceled, and we have moles, and this is moles transferred. This is the moles that are in there, moles that came from your 2.0 mole per aliquot. How do I say figs? Consensus is 3 say figs. I get so excited when you use trailing zeros after the decimal. So I'm not sure what your calculator displays, but notice that in order to get 3 sig figs, we have to use the whole 2 trailing zeros after the decimal. So now what are we going to do to get molarity of the stock? We have moles. Yep. We're going to divide that by the aliquot volume. That's it. So we take the moles that were transferred, the moles that end up swimming around in that diluted solution, 8.00 times 10 to the minus 5th moles of K2CR2O7, and divide it by the volume it came from, which was 2.00 milliliters. Now, of course, this will give us units of moles per milliliter. How do we get moles per liter?
1,000 over 1.
Yep, 1,000 over 1. 1,000 milliliters of solution over 1 liter of solution. Yep. And this will give us moles of K2Cr2O7 per liter of solution, which is perfect. And how many sig figs? 3? Yep. That's what I get. So again, to show 3 sig figs, you're going to have 2 trailing zeros after the decimal.
So do we have to put that 0.0440 mole over 1 liter, or can we just go straight to the end?
Yeah. Like Lindsay said, I probably would go, I think in my answer keys, I usually go right for that one. I usually don't put that. It's just how I think, but either one's fine. So I learned it as M1V1 is equal to M2V2, M being molarity. Here it's more general, it's concentration. This actually, C for concentration, this actually, some of you may have learned it in high school, and it works. It basically says you have stock and you have diluted, and if you take each of their concentrations times their volumes, you're going to get the same number of moles. So anyway, this actually can work, but it's a shortcut, and you can only use it when you get to Chem Chem 2. So with that in mind, do not use C1, V1 is equal to C2, V2. So yeah, I like what Lindsay said. Instead of saying, oh my gosh, 2 things of homework, say, oh, and it wasn't, we didn't have to start with the third part. So this is setting us up good for where we need to be in the lecture. So that's it. You're out early.